organic chemistry. First, we want to kind of get into definitions as to why this goes. The term organic chemistry was originally designed to mean chemicals that were, if I go back to the original definition, when you think of organic, you think of organismal chemistry. So the chemistry of living things. So for a long time, it was thought that certain chemicals were only found in living things and could only be manufactured by living things. But further on, it was discovered by the scientist Wohler, Wohler, that in fact, chemicals that we do find in our own bodies or in the bodies of other organisms can be made from substances which are not living. The first such compound that was made was urea, which when Wohler synthesized this was very excited because he said, oh, I've shown that urea occurs in urine, and he was able to make it without using, he said, man or dog. So, I know that doesn't sound very exciting initially, but it really is, because when you think that some chemicals are only life-based and others are not, and then we find out that in fact, no, we can make these chemicals independent of living organisms. That was a big achievement in chemistry. And so that was the original definition of what organic meant. Organic meant from living things. But since then, the definition has been modified. What we find is virtually all of these chemicals that are somewhat unique to living chemicals contain the element carbon. Okay, so when we talk about organic chemistry, we are specifically referring to the chemistry of carbon and its compounds. The periodic table for an organic chemist, we sometimes joke, is very much reduced. The elements that are most important to us are carbon, hydrogen, nitrogen, oxygen, and to a lesser extent, the halogens, oxygen, and phosphorus. A lot of the other elements we don't find much of a use for, except in very specialized cases. So we're really focused on carbon chemistry here. Okay. So ultimately, what we're going to be looking at here is the formation of chemicals with bonds and things like that. So let's say we're looking at chemical reactions. We know that chemicals have to collide in order to react, and then in a reaction, bonds break and or form. What is a bond? Specifically, what is a covalent bond? What is that?
The sharing of electrons?
Yeah, exactly. It's the sharing of a pair of electrons or more than one pair in the case of double bonds and triple bonds. Good. Okay. So what we're going to be wanting to know is, why do reactions occur? How do they occur? Why in particular ways? And that's what we're going to be dealing with. But the focus of this class is largely on electrons. It is moving of electrons from one place to another. There is one simple 3-word sentence that we can use to describe this entire class, and that is negative likes positive. There are some exceptions for other types of weird reactions, but it mostly comes down to something that has a lot of electrons is going to hunt down something that doesn't, and then they will share electrons. That's largely what we're going to be dealing with here. Okay, so why do we essentially distinguish between organic and inorganic compounds? It's largely because organic compounds have very distinct styles of reactions and very distinct styles of bonding, ultimately. With inorganic compounds, it tends to be a lot more varied, and so there tends to be a lot more rules here. Why are organic compounds important? Well, the first thing that we've already talked about here is they are important for life, okay? Virtually all of the major biological chemicals are organic, and this would include carbohydrates, fats, lipids, proteins. What are proteins made out of? Anyone know what those chemicals are called?
Take it away.
What's that?
Amino acids.
Amino acids. Thank you. Good. So amino acids, DNA, RNA, all of those are organic. Most of our fuels are organic. Pretty much everything in gasoline contains carbon. And so those things are burned and we derive energy from them. Plastics are organic. They contain carbon. So a lot of materials that we build Also, a lot of the new really exciting things out there in terms of materials, things like graphene, I don't know if anyone's heard about that, can be considered organic in a sense. So there are many, many applications to it. And that's why one element, carbon, gets its whole gigantic field of chemistry. There's pretty much organic, which is carbon, and inorganic, everything else. All right, it's just that important relative to other things here. Okay. When scientists were first, chemists in particular, were first starting to really study and trying to understand how organic chemicals worked, they started noticing that there were very specific arrangements of atoms in a lot of different compounds. And those arrangements of atoms, which we will call functional groups when we get to chapter 2, tell us a lot about their properties. A formula is not adequate to define this. For example, if I were to go and look at these compounds right here, these compounds both have what formula? Well, how many carbons do they both have?
2.
2. How many hydrogens?
6.
6. And 1 oxygen. So this is called a molecular formula. Okay. What does it not tell you? It tells you what elements you have, but what does it not tell you anything about?
Structure?
Yeah, structure, or to simplify it a little bit, it doesn't tell you which atoms are bonded to which atoms, right? You don't know anything about the skeleton of the molecule, what atoms are bonded to which. Okay. So this doesn't tell you anything about that. We need more information here. And these right now are essentially the Lewis structures, except that we're leaving out lone pairs. These are some pretty typical structures. Clearly, these don't have the same properties, right? Ethanol, boiling point 78 degrees Celsius. Dimethyl ether. What is dimethyl ether at room temperature? A gas, a liquid, or a solid, based on this evidence? Boiling point of -23 means it is a
Gas.
It's a gas, yeah. And an exceptionally flammable one. I don't know if any of you have seen those wart offs where you can freeze your warts off or things like that. That's full of dimethyl ether. Okay, again, incredibly flammable. But when it comes out of the container, because of that low boiling point, as it comes out, it freezes whatever it comes into contact with. It takes the energy out of your skin as it does that. So very different properties here. What's notably different here? In ethanol, the oxygen is bonded to a hydrogen. In dimethyl ether, it is not bonded to a hydrogen, it's only bonded to carbons. And these two pieces of the structure right here are going to be the fundamental groups here. That COC we'll learn in chapter 2 is called an ether. Anything with that kind of arrangement is called an ether. And anything with COH, not anything, but almost anything. Well, I don't even want to say that. A lot of chemicals with COH are called alcohols. And you'll notice the name ends in -all. Ethanol. Isopropyl alcohol will also have that kind of a group in it. So we're going to see all these types of groups. And those types of groups tell us something about their reactivity. Okay. So the types of atoms bonded to carbon that we usually find are going to be nitrogen, oxygen. Most frequent than any other element is hydrogen. And in fact, if you say organic chemistry, you usually mean carbon and hydrogen. Hydrogen is almost never left out. Okay. So carbon's not optional. Hydrogen is almost never optional. The others are, but they're usually found nitrogen, oxygen, fluorine, chlorine, bromine, iodine, the halogens. Of these 4, fluorine is the least important. Okay. The first thing we want to really focus on here, because you're going to be drawing lots of structures, and we don't want to do it the old-fashioned way we learned in 120 and 130, which tends to be pretty slow, is to learn the common bonding patterns of elements. So carbon, when it's neutral, meaning no charge, which is most of the time, the vast majority of the time. Carbon almost always is found making 4 bonds and covalent bonds. Nitrogen almost always makes 3 bonds, so long as it's neutral. And in addition, it usually has a lone pair. Oxygen, usually found with 2 bonds and 2 lone pairs. If it's found with 3 bonds, that means it won't be neutral. It'll be positively charged, as we'll see later on. Hydrogen always makes 1 bond. And X is the symbol that we use for halogens when we don't want to be specific. Halogens have usually 3 lone pairs. What rule is telling us that if we have 3 bonds, we need 1 lone pair? If we have 2 bonds, we need 2 lone pairs. What rule are we trying to follow here?
Octet.
The octet rule. Yeah, good. Can any of these atoms have more than an octet? Carbon, nitrogen, oxygen?
No.
No, none of these elements can exceed the octet rule. Fluorine cannot either. You might have remembered from Chem 130 that chlorine, bromine, and iodine can exceed the octet rule, but they virtually never will in organic chemistry. Okay?
Professor?
Yes. Question?
Oh no, sorry about that.
Okay, that's fine. So these patterns are what you're going to want to learn. And this is also the same order as what? Carbon, nitrogen, oxygen, that's the periodic table, right? Carbon is next to nitrogen, is next to oxygen, etc. Okay. All right, let me go back to my notes there. Okay, so a covalent bond is what we get whenever a pair of electrons is shared between 2 atoms. So a typical example of this, the simplest example we can probably think of, is hydrogen molecules. I have a hydrogen with 1 electron, another hydrogen with 1 electron. The hydrogens would like to share electrons here. So we want to balance out our spin. One of them will be spin up, one will be spin down, and they want to come together to form a molecule. If they're too far away, they can't really feel each other here, and so the energy is relatively low. If they are too close, the energy is too high. Let's see if we can understand what this means here. First of all, why would 2 hydrogens want to come together? What's the basis of the attraction? What is attracted to what when these 2 hydrogens come together? The what is attracted to the what?
Electrons? Or they're trying to complete like a, I guess their ring, right? The electron ring.
I would use the word ring here. So what part of hydrogen is negative? What's the only part of hydrogen that's negative?
Electron.
The electron. What part of hydrogen is positive?
Nucleus.
Good, and that's true of all the atoms, right? The electrons are always negative, the nucleus is always positive. So the attraction is this hydrogen atom's electron is attracted to this hydrogen's nucleus, and vice versa. This hydrogen's electron is attracted to this hydrogen's nucleus here. And so by coming together, again, this is negative likes positive, we get a lower, more stable energy. So very important to understand. When we use the word stable means very reactive or not very reactive. What do you think?
Not very.
Not very reactive. Good. So do stable things usually explode spontaneously?
No.
No. Right. Hydrogen isn't the most stable compound in the world, or stable thing, because it will react violently with what? To make water. Hydrogen reacts with
Oxygen.
oxygen. Good. But it can be relatively stable. Now, is the most stable point the highest energy or the lowest energy? Lowest energy, right? Okay. So what is this showing me here? The lowest point is when the 2 hydrogens are how far away from each other? 0.74 angstroms. Angstroms are kind of an old way of doing this. An angstrom is 10 to the minus 10 meters, which would be what, 0.1 nanometers, 100 picometers. Okay, so that's the typical distance between those guys there. Okay. There. So how do these terms relate to each other, potential energy and stability? So the higher or the lower the energy, the more stable. The more stable corresponds to energy, the more stable. Okay. So if we go ahead and we look here, we want to keep these terms pretty much understood as generally equal. So more stable generally means lower energy. And less stable is higher energy. When we use the word energy, we're usually referring, for example, to the Gibbs free energy, which we'll talk about later. We talked about that in Chem 140. Okay. And usually this typically means less reactive versus more reactive. Although those reactive ones, that can be a little bit more tricky. Okay. So we're saying that hydrogen is at its most stable, when the bond length is about 0.74 angstroms. Why does it suddenly get much less stable when the bond length gets smaller? Why aren't we going to want to see it, for example, at 0.35 angstroms? What would be bad about that?
The two nuclei are too close to each other.
The two nuclei are both positively charged. And as you try to put positive charges too close to each other, they are going to repel. Good. As you try to put positive charges too close to each other, they are going to repel. Humberto, be careful because you're mute. Yes. Okay. We'll talk in a second, Humberto. We need to practice with your microphone because it's not working very well. Okay. What happens as the distance gets greater and greater? Well, as the distance becomes too great, there's no longer an attraction. Too big of a distance means that the electron here can't see or feel this hydrogen's nucleus. And so eventually it's just like you have two separate hydrogen atoms that have nothing to do together. So this is kind of a driving force here. What happens when you bring together two atoms and form a bond? Energy-wise, what always happens whenever you form a new bond? Is energy taken in or is it given off whenever you form a new bond?
Given off, right?
It's always given off. Good. If we used the words endothermic and exothermic, what's the correct word for making bonds?
Exothermic.
Exothermic. Good. Good. And if you try to just break bonds and only break bonds, that's always endothermic. You always have to put heat in. You always have to put energy in. Good. So this reaction will give off products. How much will it give off? Well, take a look here. You're starting with two separate hydrogen atoms. When they come together, they will give off 436 kilojoules for every mole of hydrogen. Okay. The lower that number is, the more stable, so to speak, as far as this goes. So the more negative means very, very stable. Okay. So we already talked about here what's keeping them at the attraction there. Okay. So going into this, as we've already said, protons are positively charged, neutrons also are in the nucleus. They're neutral. For right now, we can largely ignore the neutrons. Neutrons are going to be important later because of their effect on mass and their effect on spectroscopy, a nuclear magnetic resonance spectroscopy, chapter 15. That's a long way off, though. Electrons are found outside the nucleus. What kind of hypothetical structures, what kind of things do we say electrons are found in? They're found in, anyone know? Starts with an O, called orbitals, right? We say that electrons are found in orbitals, okay? Like 1s orbitals, 2s orbitals, things like that. So, but they are generally outside of the electrons. Some of the electrons are close to the nucleus. We call those core electrons. And then the ones in the outermost shell are called the valence electrons. For chemical reactions, first of all, let's look at carbon. Carbon has how many electrons? Let me open up my periodic table real quick. Where did you go? Let me my periodic table real quick. Okay, carbon electron configuration 1s2, 2s2, 2p2, right? So it's got configuration 1s2, 2s2. So it's got 6 electrons. So electrons are in the core, okay? And we have some 2s electrons. Those are 6 electrons, and these are valence. Okay. I'm sorry, Humberto, you're really echoing a lot. So don't unmute yourself for right now. I'm sorry about that. If you have any questions, type it in the chat, and I'll try to address it there. And then we'll see if we can figure out what's going on a little bit later. But it's producing crazy noise everywhere. Is everybody else hearing that, or is it just me? Okay, yeah. So we'll have to figure out what's going on with your signal. So anyway, if we look at carbon, oops, where did that go? Good. We said carbon has a 1s2, 2s2, 2p2. That's its electrons configuration, which is the same as helium, 2s2, 2p2, which means there are how many valence electrons? There are 4. Why are these so important? What do we use the valence electrons for that we don't usually use the core electrons for? These electrons are used to make
Bonds.
Very good. We don't usually see that with the core electrons. The core electrons would be the 1s here, okay? Anything in 1s would be core. For carbon, nitrogen, oxygen, fluorine, anything in group 2, the 1s electrons are core, and everything else is a valence electron, okay? How can you easily find the number of valence electrons? It's the same as the group number. So this is group 1, group 2, group 3, 4, 5, 6, 7, 8. So carbon is in group 4A. I don't have that labeled right here, but 4 valence electrons, nitrogen has 5, oxygen has 6, etc. Maybe I'll find another periodic table there. Okay. So as I said here, this is how you can figure it out by looking at the electron configuration. Let's take a look at phosphorus. Phosphorus's electron configuration is neon. Followed by what? So this is the third row. So this is 3s, 2, 3p, 3. So phosphorus has how many valence electrons?
5.
5. Yeah, 2 plus 3. Good. And if you looked at the group number, phosphorus is in group 5. So you don't even have to write out the electron configuration. You just look at the periodic table and you see it's in group 5A. Okay. Good. And so this is a simple version of that with the periodic table with the group numbers listed. What is the only element here which is wrong? In other words, which does not give you the right number of valence electrons if you look here. So in other words, nitrogen is 5, phosphorus is 5. Which is the only element that doesn't work that way?
Helium.
Helium, good. Helium has how many valence electrons?
2.
2.
Very good, only 2. Well, let me turn that off. Good. Only 2. Do you think we care about helium in this class much? Not for reactions, because it doesn't react with anything. So we can forget about helium then. Okay. We want to quickly review drawing Lewis structures. But the nice thing about this is I've already given you this right here. In most compounds, carbon makes 4, nitrogen 3, oxygen 2, etc. So we usually want to use that as a guideline. But for more difficult compounds, we need to remember the old way of drawing Lewis structures. Okay? So for the simplest ones, these are ones that don't have any charge. All we want to do is draw individual atoms. We use dots to represent the valence electrons and only the valence electrons. And we put the atoms together in such a way that we end up with an octet. In other words, each atom other than hydrogen surrounded by 8 electrons. So you'll notice nitrogen here has 5 valence electrons. It would like to have 8. And so if it shares with 3 different hydrogens, each one of them brings an electron with it. And that gets us to 8 valence electrons. That's an octet. Nitrogen deceives itself into thinking it has 8 electrons. In reality, of course, it only has these 2 exclusively to itself. The rest are shared, but that's okay. Okay. Let's say we want to draw C2H2. Okay, so C2H2. Each carbon has 4 valence electrons, right? And each hydrogen has 1 valence electron. How can we make everybody happy here?
Is there a double bond between the 2 carbons?
So like, for example, I could share those 2 and these 2, right? What else?
Oh, maybe also the bottom ones too?
Okay, so that would be a triple bond, right?
Triple bond, yeah.
Okay. And then what else? We could share.
The hydrogen ones.
We could share those 2 and we could share these 2. Good. And so then that would give us the 2 carbons with a triple bond. So there's 1 pair, here's a pair, here's a pair. And there's a pair between those hydrogens and these hydrogens. Which could be, how could we rewrite that? We can replace each pair with a straight line. Because remember, a line just stands for a pair of electrons, a pair of bonding electrons. Good. So either way is acceptable. I prefer this way. It's much easier than trying to count dots. You'll agree. So all the electrons are shared as far as this goes. Anyone know the name of this important chemical here? It's called
ethylene.
acetylene is the common name. Ethylene is also ethine is the other name. Yeah, but acetylene is the simplest name. And what is acetylene used in more than anything? It's a fuel for blowtorches, if you know. Okay. So that's one way to do it for some easier compounds. For more difficult ones, we can come back and we can use the ways that we learned in Chem 120 and 130. And I'll do a couple examples of those as we go a little bit further. Okay. Let's say that we have atoms which have an unbalance in the charge, where they have formal charge. What word do we call atoms that have a charge? We call them
Ions?
ions. Good. They're ions. Okay. Now, the atoms in these guys here can have unbalanced charge in many of our different compounds here. Okay. What we often want to know is, if a molecule does have charge, which atom does that charge reside on? So what we're going to be doing here is we're going to look at calculating formal charge, something that you did in Chem 130 before. Formal kind of means it's a formalism. These values are approximate, they are not real. They are just kind of used to guide you to knowing where you might find negative and positive charges. And sometimes the formalism is totally wrong. But we want to know this process because it will help us out in a lot of different ways as we go forward. Okay. So the way that we calculate formal charge is as follows. We look at a given element and we ask ourselves, first of all, what is its valence number? Carbon is in group 4A. It has a valence of 4. And then we look at the molecule here and we go, well, how many atoms does it seem to have here? The way that we deal with this is we say any electron that's in a bond, we put 1 electron to each atom. So carbon gets 1 electron here, 1, 1, 1. So there's a total of 4 electrons that belong to that carbon. We take that number and subtract the valence, and that is its formal charge. So 4 versus 4. Let me write a formula for that because it's probably easier to do it with a formula. Okay. So this is the process way, the way your book takes you through it. Okay. But the formula would generally be as follows. Formal charge equals so the valence number of the atom minus the number of bonds on the atom minus the number of lone pair electrons. Okay. And you want to get used to seeing these patterns. So the way this carbon did it, it makes sense. Carbon has a valence of 4.
4.
How many bonds is it making?
4.
4. How many lone pair electrons does it have?
0.
0. So it's a 0 formal charge. Good. Oxygen is group 6 of the periodic table, right? So it's got a valence number of 6. That looks kind of ugly. Let me take it away a bit. How many bonds is oxygen making?
1.
1. And how many lone pair electrons does it have? 2, 4, 6. Not the number of lone pairs, but number of electrons is 6. So 6 minus 1 minus 6 is negative 1. Okay. And so we indicate that by either writing minus or minus in a circle. Either way is fine. Which will I do? Depends on how I'm feeling. Some days I put a circle, some days I don't put a circle. Usually you put a circle if there's any chance that it could be misunderstood as a bond or something like that. But you'll see both, circled and uncircled. The hydrogens also all have a formal charge here of 0, right? Their valence number is 1, they're making 1 bond. So long as hydrogen's making 1 bond, formal charge is 0. Okay. So that's why, this is just another way of rationalizing it. I like the formula myself to do it. Okay. Now, is the sharing equal between the atoms? So when these come together, do these atoms actually share the electrons equally? Does this pair share equally or not? To understand that, we have to get into electronegativity. Remember electronegativity, right? So ultimately, when we think about this here, what do we think these orbitals look like? Are they totally equally shared, or are they skewed towards one area or more towards another? And so we're going to have to look at those orbitals a little more closely as we get there. So right now, these are hypothetical questions that we're going to start trying to answer as we go a little bit forward here. So first, the covalent bonds that we deal with are either polar or nonpolar. When we say a covalent bond is nonpolar, that means the electrons are sharing electrons evenly or approximately evenly. If they are polar covalent, then one of the atoms attracts electrons more than the other. Okay? So when we talk about electronegativity, that is not only how strongly an atom attracts electrons, it's probably better to say how much it attracts shared electrons, not just random electrons, but electrons in bonds. Okay, that is really what electronegativity is. We should know by memory the electronegativities of pretty much the top row and hydrogen, which is easy because we know fluorine is the most electronegative and its value is 4.0. That's called its Pauling value. And then what happens as you move to the left? You just subtract 0.5, right? So fluorine is 0.5, oxygen 3.5, nitrogen 3.0. I would not memorize lithium, beryllium. I wouldn't bother with most of these two, but the most important ones are boron over to fluorine, hydrogen, and then probably phosphorus, sulfur, and chlorine. Okay. Now, there are other factors, by the way. Like, for example, you might say, well, carbon and sulfur have the same electronegativity, right? So according to this, they should be sharing equally. But as we will see, there's another complication. What do these have different? There's a number of differences between them.
Valence electrons.
Yeah, much more electrons, and very importantly, there's a size difference, right? Sulfur is much larger than carbon because it's in group 3. So even though they have equal attraction for electrons, the electrons are going to spend more time near sulfur because it's just bigger. Imagine trying to go around an element. You know, the larger size, larger volume is going to make a difference, and we'll talk about that more as we get further in the class. But for right now, this is going to tell us largely about how polar they are. So equal would mean that the numbers have to be exactly equal. We're going to say anything with a difference less than 0.5 is equal. So very important, carbon, hydrogen are going to be considered nonpolar or polar. Is the difference 0.5 or less? I mean, less than 0.5? It is, right? The difference between carbon and hydrogen is 0.4. So we will consider that nonpolar covalent. Carbon-nitrogen, on the other hand, the difference is 0.5. That's just enough to be considered polar. So 0.5 or higher is considered polar. Okay. So electrons tend to be skewed towards the most electronegative atoms. So carbon with carbon is totally polar, right? Same electronegativity. Carbon with oxygen is polar. And we say that carbon has a partial positive charge and the oxygen has a partial negative, because oxygen is more electronegative than carbon by a pretty significant amount. By how much? Carbon is 2.5, oxygen is 3.5. The difference is 3.5 minus 2.5 is 1. That's definitely considered polar. Okay. Here's something new that we will get into towards the end of the semester. Carbon with lithium. Well, that should seem strange, because why? Why should that seem strange when you first talk about it? I'm sure you've never seen carbon lithium before.
Because it usually goes to the increasing electronegative charge.
Carbon usually does, yes. But what about these two atoms being bonded is strange in the first place? What's weird about those two atoms being bonded? Carbon oxygen's not. What?
They wouldn't complete their octet.
That's true. There's other atoms, though. Imagine there's other atoms, though. Hydrogen, hydrogen, hydrogen. So that is true, but there would be other atoms. It's what is lithium that oxygen and carbon are not? Lithium is a metal, right? And usually what are in covalent bonds? Usually covalent bonds are what with what?
Metal and non-metal.
Non-metal, non-metal, yeah.
Or non-metal.
Covalent bonds are almost always non-metal, non-metal, right? This is called organometallic, which will be a very big deal in organic chemistry. So when we talk about bonds between metals and non-metals, that's a different kind of a compound here. If there's a metal with carbon, this is polar because why? Carbon's electronegativity is 2.5. Lithium, though, is way down at 1.0. So this time it's a little backwards. Carbon is more electronegative than lithium. Now, the question we have then is, well, why did I draw it like this instead of like this? We really shouldn't draw it like this. We should draw it like this. It's because the type of attraction isn't really covalent. It's more almost ionic. So this is an important thing to understand when we talk about bonding. Bonding is a continuum. There are rarely purely covalent bonds and purely ionic bonds. Most bonds fall somewhere in the middle, where they have a very ionic character to them, okay? So the only times you have absolutely purely covalent is when the elements are exactly the same. So this is a totally covalent bond. Carbon-hydrogen, almost totally nonpolar because their electronegativities are very close. Why is sodium chloride almost totally ionic? Because the electronegativities are very different, very far apart. So the farther apart they are, the more ionic they are. If I said carbon-oxygen, I would call that a polar covalent bond. Lithium-carbon, that's really hard. I would say that that bond, the cheating way of dealing with this is to say it has a very high ionic character. Very, very close to an ionic bond. Very high ionic character. Nitrogen, lithium, very, very much close to an ionic bond. So when we look at bonds between nonmetals and metals like this that are covalent, you have to always look at them with some skepticism. You say, yes, I've drawn it as a covalent bond, but it's really closer to ionic, okay? Does anyone know what the most polar covalent bond would be? The most polar covalent without being called ionic. It would be between hydrogen and fluorine. Hydrogen fluorine is considered the extreme polar covalent. So what's the difference between hydrogen and fluorine? It is 1.9. So that means anything that's 2.0 or greater is usually considered what? 2.0 or greater is usually considered ionic. If you have to put it into the bin of nonpolar, polar, and the other, it's that way. So let me just write those values down. So this is usually the way this goes. We say nonpolar covalent is difference of electronegativity of between 0 and 0.4. Delta En, again, means difference of electronegativity. You take one atom and subtract the other. Polar covalent is between 0.5 and 1.9. So difference of electronegativity of, greater than 2.0, greater than equal to 2.0 is ionic. That's our usual way of doing it. So ionic is the extreme polar of polarity. Okay, that's usually what we're going to be using as our base values here. Any questions so far about electronegativity, polar, nonpolar, that kind of thing? No? Okay. So this should all still be reviewed, I'm hoping. Okay. Atomic orbitals. So now we jump a lot in this chapter because this is just review of different topics from the GChem. So in Gen Chem, remember that we talked about quantum mechanics. When we talked about quantum mechanics, that is the properties or the interactions of things that are very, very small, like electrons, atoms, molecules, things like that, okay? Remember that we said that light, we talk about light a lot when we talk about quantum mechanics. We said light is like both a wave and like a particle at the same time. That was called the wave-particle duality. You'll then remember that we said, well, wait a minute, matter is kind of like that too. Like, for example, we can say electrons are kind of like particles and they're kind of like waves. Do you remember what we call the wavelength associated with electrons or with particles? There was a word for that. It was named after someone. Anyone remember?
It hurts.
Which one?
Hertz or frequency?
Not hertz. No, that's the name of our frequency definition. It was called the de Broglie wavelength. De Broglie or de Bro. You don't need to know that, but the de Bro wavelength. You should have seen that in Chem 120. You don't need to write this down, but de Broglie. But I think it's pronounced de Bro. Anyway, that tells us the wavelength of electrons. Do we have wavelengths that are measurable as people? Are we moving around as waves? No, because we are much more massive, right? Electrons are the things that have wavelengths, and nuclei have wavelengths. For us, our wavelength as people is about 10 to the minus 31 meters. You can't see it. It's so small, it's essentially non-existent. Okay. Now, each of those electrons has associated with it this wavelength. And then we have these things called wave functions, which are used to tell us something about the behavior of those different electrons. Do you remember back in Chem 130 when you went through and you said, well, let me just add a junk paper because this is something you don't need to write down. But does this look at all familiar? when we said, oh, this electron has these values here. Does that look at all familiar? Do you remember what this means? N equals 2. What N equals 2 tells us is that the electron is in the second shell. Okay? It's in the second shell. How about L equals 0? That ring any bell?
Is that the groups?
It's the orbital types, the subshell. 0 means S. So if I drew this, this means the electron is in a 2s orbital. Okay. M sub L is which orbital you're in. S's always come in sets of 1, so there's only one of them. And what is plus 1/2? This can be plus 1/2 or minus 1/2. Do you remember what that is?
The spin.
Spin. Good. Plus 1/2 means spin up. And minus 1/2 is spin down, if you remember those here. Okay. So these numbers go into an important thing called the wave equations, which we use this symbol for. Okay. The wave functions. This is way beyond anything we do here at Rio Hondo. I don't know, maybe Professor Vaca gets into this. But in general, this is the next couple classes. This is physical chemistry. So we're not going to get into the wave equations here, but these things figure into them. And there are all these complicated, crazy equations with sines and cosines and things like that in them. Okay. And those equations give us the shapes of these things. And these are called orbitals. You remember orbitals, right? What kind of an orbital is this right here? An s orbital, a p orbital, a d orbital? Do we remember?
Maybe S.
It's S, right? Simple spheres are s orbitals. Good. Okay. So what are they? They are the regions in space where you are most likely to find an electron. Okay. An orbital is a region in space where you are most likely to find an electron. Okay. So we can identify them by their shape. This is an s orbital. Usually the way we do this is an orbital is meant to represent where you are 90% likely to find an electron. So an electron will usually be within this space. If we say it's in an s orbital, it's usually here. But can it be out here? It can. Can it be somewhere out over the Pacific Ocean? It can. It's just saying 90% of the time it's here. Okay. Good. Okay. So, as I said, electrons have a wavelength. They can behave both as particles and as waves. Okay. We have theory and experiments that back this up. We don't just make this up. It sounds crazy, but it's kind of true here. And so we can say, just like a wave on these lakes or any kind of a body of water, we say an electron has a wave function that can be positive in some places and negative in other places. So if we think about electrons, there are positive and negative parts to it. And where the wave function goes to 0, we call that a node. Okay. What do we call if we think about this in trigonometry, what do we call this value here? How high above this level it is? So the height of this is called the what? It starts with an A.
Amplitude.
The amplitude, good. So a node is where the amplitude is
0.
0. Good. Okay. This is a different type of an orbital. What is this one for? S, P, D, or F?
P.
P.
This is a p orbital. Good. A p orbital looks like two tiers that are drawn upside down. One is upside down, and then they're joined right in the middle. Okay. And what we say about the wave function here is that this side is the positive side. That is, the wave function is positive. Here the wave function is negative. And right here at that spot, the wave function is 0, where it's a node. Okay? That doesn't, now the way we usually think about this is we can say, all right, that's where the electron has 0 probability of being. It can't be there. But the best way to imagine is the wave just kind of disappears off to 0 at that point, and then it crosses over here. Very, very important. This positive and this negative has nothing to do with charge. An electron is always what? Always negative, right? Always has a negative charge. So if it's up here, it's negative. If it's down here, it's negative. The only difference is it's just telling you the amplitude of the electron at this point. Is it a positive amplitude or a negative amplitude? That's going to be important because it's going to tell us whether different things come together in bonds or what we call antibonds. Okay, the signs are going to be very important of that, but it has nothing to do with charge. Okay, now right now the node looks like only a space, but it's really a whole plane. Okay, in 3 dimensions there's a whole plane right there. The electron's either above or it is below. It is not generally found both. Okay. Now I'm running at it looks like it's about 2:45 at this point. So I think you have enough information to be able to do the first set of homeworks.